Hello and welcome to Introduction to Astronomy. I'm your instructor, Dave Kirsch, and I'm very happy to be your instructor this semester, even though I unfortunately don't get to meet you. But this semester we have quite a lot of very interesting content that we're going to be going through and a lot of interesting material to learn. So for this class, we're going to dive right in. We're going to start talking about what sort of things you find out in space, what is the layout, like what's your cosmic address, where do you really live? And to begin with, though, we're just going to talk about some course basics, okay? So let's lay it out. What can you expect from this course? How is this going to work? Hopefully you've looked through the D2L site and you've read the basics. So let's go over that a little bit before we proceed into any actual material. So first off, do make sure you've read that course outline. Okay, the course outline contains all the necessary information about the course. It lays out the rules for the course, the rules that you have to follow, but also the rules that I have to follow. All right, so do make sure you've read it. The important stuff, I guess, for now is that lectures, as you are seeing, lectures will be Fridays, 6 to 9 p.m. That's our booked time slot, but I'm going to be pre-recording the actual lecture component. All right, and posting on YouTube, again, as you are obviously aware since you're watching it. So that will be posted. Generally speaking, they're about an hour long. So you're going to watch the recording, and then once the recording is done, we're going to work together to do the live quiz, as you will shortly experience. So the live quiz, we're going to have a live Zoom session. And really, it's just, you're mostly going to be using the chat feature in Zoom to go over the quizzes with each other, and I'll be there from 7 to 9. That'll be when it's open and available. And that's normally more than enough time. Some people like to stay the full time, some people don't. It doesn't really matter, but do show up. I'll be giving hints and I'll be helping and making sure, hopefully, that you get full marks on those quizzes, which are worth 30% of your final grade. So you'll definitely want that. But working together mostly and helping each other mostly, that's what I want to see for those quizzes, so that you can work together and come to the correct answers yourselves with a little bit of help from me. And but keep in mind, those are, relatively speaking, mandatory. If you miss it, it's not the end of the world. You can still do the quiz. But if I make like an announcement at the start of the live time, then I'm going to consider that announced. Okay. Generally speaking, it's not going to be a secret. I'll also announce on the course website, but you really should show up for those live quizzes, those live sessions. So the evaluation, you can see the breakdown, 30% for the quizzes. So those are very important. The research report, 20%, 2 Q&A discussion activities, a total 10%, and 2 tests for a total of 40%. So each Q&A is worth 5, each test is worth 20%. So that's our breakdown. So let's take a little bit more of a look at these components. So the quizzes, assignments, homework, whatever you want to call them, each class we're going to have one. Really, it's a take-up of the material, and it's not just testing you. It's also where you're really going to try and put the information that I just told you to use to hopefully come to an understanding of it. All right. Generally speaking, if you're told something, you don't absorb it all that well. What really helps is to actually use it, is to think about it, digest it. So the quizzes are designed to get you to think about the material you just heard in the lesson, hopefully directly after hearing the lesson, just like it would be for in class. And so those are like little exercises and activities that will get you to really think about it. If you are not able to make it directly at that time, the 7 to 9 time slot, then I do make sure that they are open for a little bit extra. So since we have a Friday class, our quizzes will be closing Mondays at 7 p.m. Okay, so the next weekday, excluding Saturday, Sunday, at 7 p.m. All right. If we had like a Thursday class, they would be closing Friday at 7 p.m. But since we have a Friday class, we're going to close them Monday at 7 p.m. All right. So you will have actually a few extra days where you can get them done without penalty. But if you do them after after Monday at 7 p.m., even if you do it Monday at 7:30 p.m., 0. Okay, no mark for that. The system will actually assign you a mark, which unfortunately I can't stop it from doing, annoyingly. It'll assign you a mark, but I will zero it out later. So do not get them done late. Get them done within that window. Realistically, hopefully you're getting them done Friday night, right after the lesson, while working with your peers and me, but get them done at the latest by Monday night. And you can find them fairly easily under the quizzes section. in assessment. And so there are 11 total, and I will drop the 2 lowest marks. So that means it's basically going to be 9 quizzes determining 30% of your final mark. Since I'm dropping the 2 lowest, I consider that sort of a built-in forgiveness for, stuff happens, especially these days. Stuff happens. As a result, I won't be doing any extensions or anything like that. Frankly, you've got a fair amount of days to get them done anyway, Saturday, Sunday, and Monday, right? So yeah, don't get them done late. So let's see. The other components are the report, worth 20%. There are full instructions. The report is fairly specific. I give fairly specific instructions broken down by section. Those section headings you have to have in your report, and you just discuss what each section is supposed to be in your report. So it's fairly laid out for you. Should make it easier than just doing an essay. I mean, some people like doing just an essay, whatever you want, right? But me personally, I tend to like it when it's a little bit more clearly broken down, and that's what we're going to be doing this semester. So make sure to read those instructions. I'll be marking it based on how well you follow the instructions, okay? Then we've got the 2 tests, each worth 20%. So 40% total of your final marks coming from the test. They will be fully multiple choice, and you're going to have about, I think it's an hour to do them, all right? But I'm going to make sure they're open for a couple days. So I think it opens October 29th at 8 and closes October 30th at midnight. All right. So you're going to have a couple days. If anything goes wrong with those tests, then I could perhaps reset them. But that's why I really hope you get it done on October 29th, not the 30th. Right. So get them done early. It only takes an hour. It's 30 multiple choice questions. So they're not that bad. All right. The final is non-cumulative, which means it only covers the material since the midterm. So 2 tests, midterm and final, each covering, I think the midterm covers 5 and the final covers 6 lessons. And then there's the Q&A discussion activities, each worth only 5%. So for those, what you're going to be doing is you're going to be posting 2 questions based on the lessons that we've had to that point. So the first one comes out just before the midterm, a week before. The second one a week before the final. It's supposed to be a chance for you to discuss with each other, ask interesting questions, do a little bit of research to answer your peers' questions, and also to study a little bit for the test, right? To really think about what was taught. So when you ask questions, you're not trying to make up test questions. You're asking questions of like, hey, I didn't understand this part of the lesson, or hey, I thought this was really interesting. What do you think would happen if? Something like that. The sort of questions that you would ask in class. Okay, so you're going to be posting 2 questions individually. So we are going to be using the discussion boards heavily. So you're going to make 2 different discussion board posts with your questions, and then you're going to answer 2 peers. And in science, we don't want to answer with opinions, right? Well, I think, off the top of my head, blah. That's kind of useless when it comes to science. What we want is to do a little bit of research. So when you attempt to answer your peers, you're going to have to provide a source. You're going to do a little bit of research on their question and give them an answer. Doesn't have to be too in-depth, right? But generally speaking, I think those are actually really good. People have really come up with some interesting answers in the past, done some very interesting research. It's just a chance to look into something interesting. There is a sequel course to this, Advanced Topics in Astronomy, which I teach, and there I have my students do the Q&As every week. Because generally speaking, they turn out really well. People ask some very interesting questions and research some very interesting stuff. All right, so they are a chance to help study and to review, along with just a chance to learn about some interesting astronomy. So we do have a textbook for this course, and in the weekly schedule, the sections that you should be reading are assigned. Now, this will not be directly tested, but it is free. It is totally free, which is delightful, and it is very useful. So when we talk about something, you can then go do a little bit of reading, or hopefully the best time to do a reading on these sorts of things is before the lesson. So look at the readings, do the readings, and then watch the lesson, and you will get a lot more out of the lesson. Because if you've already read about something, to hear it discussed, it'll be a lot clearer to you. Okay, so you can download the PDF or you can just access it online. It's free. and it's very helpful. But again, I won't be testing it, okay? So I'm going to be posting the slides. You'll get those. And we've got our live, we've got our live after sessions, and we've got these recorded sessions. Do make sure to review the slides and do the textbook readings, right? And that'll be what you need to succeed. So again, as I mentioned, there are a lot of discussion forums that I've posted on the website. You will be using the discussion forums. There are bonuses for doing so. The more you do so, the better. But that is how I want you to be asking questions. In an in-person course, you would be raising your hand, and I would be answering your question to the benefit of the whole class. But here, that's not happening. So here, I want you to be posting your questions so that everyone can see the question and the answer. Most people in this class, I mean, you're sitting there, you tell me, are you taking an astronomy major right now? No, you're not, because no one here is. There is no such thing at Ryerson, okay? Everyone here is new to most of this material. If you have a question, probably everyone else has that question too. I know it doesn't seem that way. Normally it seems like, oh, nobody else cares. If I put up my hand, I'm going to be embarrassing myself. Well, first off, this is an online forum. That doesn't really happen. But second, no, everyone will have pretty much the same questions. If I've said something unclear and you want clarity, or if there's something I didn't explain and you want more, or if there's just something you're curious about, please post it in the forums and we will talk about it there, and then everyone will benefit. And it's to help propel that, that's why I'm going to be offering the bonuses. In fact, if you send me an email, unless it is totally personal and private, like, oh, hey, there was something wrong with my mark, or oh, hey, I have a personal issue I need to talk about you with, unless it's personal and private, I will simply tell you, post it on the forum. And so don't forget that, because a lot of people end up sending me a question the day before something is due, and my response, unfortunately, is post it on the forum, and then guess what? They don't have time to get it done. They never get their answer before the thing is due. That's a shame, but please, that's why I'm putting this out there right at the beginning, as clear as I can. But let's all post in the forums, and we'll all benefit from each other's efforts. So the goals of this course, this is an exciting course with exciting material. The goal is to understand the universe. And well, that's a big goal, but it's an exciting goal because the universe is a very, very big and exciting place. We want to understand what's out there, not just what's around the block, right? Not just a little bit of what goes on Earth. We want to understand everything. And there's a lot to understand. The way we figure all this out is with science and the scientific method. And we can appreciate both what's out there, and we can appreciate the fact that we have figured all this out. The fact that I can tell you about distant stars and galaxies, that's incredible. But we as a species have learned all this. It's one of our greatest achievements, and it's well worth understanding. We want to learn about an evidence-based scientific worldview. I think we all know the world these days is not all that concerned about facts. And that's a problem. That's a loss for everyone. The more we embrace evidence-based, the more we embrace really learning about something before you talk about it, the more we will gain from the world. The truth is, we're talking about the whole universe here. We're talking about some very complicated stuff. My goal, of course, is not to blow you away with the complications. Again, most of you are coming in with the same background on most of this stuff, which is not a lot. And I'm cool with that. All right, we're all going to be cool with that. We will be doing some math here and there, but that is not my goal. Frankly, I see that as an aside. I see that as a necessary and helpful sort of tool, but that's not the goal. The goal is to really understand as much as we can what goes on in our real, amazing universe. So I'm not going to try and blow you away with hard, useless work. Everything that we do in this course has a reason. We do our lessons because we want to learn about interesting stuff. We do the after-class quizzes because we want to cement that knowledge and test how well you understood it for your own benefit. You can find out, did you understand it very well? And the tests are basically the same idea. How well did you understand something? The report is an opportunity for you to learn about something interesting based on your own choosing and dive deeper into it. So these are all opportunities, all right? So what are you going to need for this course? First off, an interest in astronomy. I sure hope you are interested. Hey, if you're not, I'm going to make you interested, all right? That's my job. You will need a scientific calculator. It'll have to do some basic math. but it should be a scientific calculator. Scientific calculators have the option to do scientific notation really easily. With a scientific calculator, let's say you need to put in some big crazy number like 6 billion trillion. What you can do is you can push 6, and then you hit EXP, and then you put the scientific notation exponent. So if I wanted to put 6 times 10 to the 27, I don't have to type in 6 times 10 to the power of, where is that? 27. No, I just hit 6 EXP 27. Very fast, very easy. You're going to want to get to know that because we will be doing a little bit of math, and it will matter. We do need these numbers, as we will talk a little bit more about later on. So let's get started. All right, let's get into it. Let's get to some astronomy with what is the universe made of? And that's a big question. So a lot of what we're going to talk about in this course is stars. Most of what we see in the universe really is stars, is light coming from stars. And there's a lot we can learn about stars. Here we see a picture of a well-known star to us, the sun, a little bit artfully enhanced around here. The sun has a certain structure. It's got sunspots that we can track. We can learn about the interior of the sun by using basic physics and by observing the exterior. Unfortunately, we're never going to really dive in and learn about these different layers, but like physically dive in. It's a little hot, but nonetheless, we can try and understand it. So we've got stars. These are large glowing balls of gas. Actually, it's not really gas. It's so hot that the atoms are completely ionized. What that means is normally atoms have like a nucleus and then electrons flying around. But when something gets so hot, the electrons come breaking off and you've got something totally ionized that becomes a plasma. You ever seen a plasma ball? One of those little things that you put your hand on, it looks like lightning bolts in there? Plasma. Stars are fully plasma. But they're hot enough to fuse. Nuclear fusion is how they generate their energy, the heat and light that comes pouring out of the sun that allows life on Earth. And we'll talk a little bit more about that. We've got the planets around our sun that we will talk a little bit more about. We've got Mars. Well, we've got the whole solar system that we're going to take a look at. Mercury, Venus, Earth, the third rock from the sun, Mars, Jupiter, Saturn, Uranus, Neptune. They're all remarkably unique, and each is very, very interesting. This here, in case you can't, this is the biggest mountain in the entire solar system on Mars, and this is the biggest canyon, 10 times deeper and longer than the Grand Canyon on Earth. Even Mars, one of the smaller planets, has some amazing features. All right. These are relatively large objects that orbit a star. They don't glow. They shine by reflected light. If there's no star to illuminate them, hard to see them, all right, because they don't actually make their own light for the most part. They put out a little heat, but that's about it. In our solar system, we've got the rocky planets. Neptune and Uranus are called, and yes, it's pronounced Uranus. These are called ice giants because they have a lot of icy compounds in them. Jupiter and Saturn are called gas giants because they mostly have gas. And we're going to take a closer look at all these things. Around some of the planets, we've got moons. If you think this is our moon, it looks a little bit like our moon. It's bigger. This is Ganymede. This is the biggest moon in the solar system, and it orbits, of course, the biggest planet, Jupiter. Moons are also called satellites. Satellite is anything that orbits. So moons are satellites. They are natural satellites. Of course, we put up artificial satellites as well. So any object that orbits a planet is a moon. And not all planets have these. Mercury and Venus don't have moons. Mars has 2 little captured asteroids. And then there are, of course, the asteroids. Asteroids come in a variety of sizes. Some of them are pretty impressive. Some of them are pretty dangerous. So these are generally rocky and relatively small. They don't have a lot of gravity, so they don't really end up forming spheres. They mostly look like lumps. If something gets really, really big, then it has the gravity to make it to make itself eventually into a sphere shape. But asteroids are a little bit smaller than that. So here we see a little bit, this is a comet, right? You notice the 2 tails? So this is pointing directly away from the sun. And we'll talk more about comets as well. All right. So comets are relatively small as well. They're icy. When the sunlight hits them, it melts them, and it propels a little bit of charged particles, ions, away from the sun. And so the comet is not traveling this way, by the way. It's traveling some other direction, but the sunlight pushes material straight off the comet as it melts it, which is very interesting. In our solar system, we've got all this going on. It's a very complex place in our solar system. All right. Another name for the sun is Sol. So solar system is the planets, asteroids, comets around our sun. So Mercury, Venus, Earth, and Mars. Then we've got the asteroid belt, Jupiter, Saturn, Uranus, and Neptune. And then out there, we've got the Kuiper belt full of comets. This is what we find around our sun. And our sun is just a star. So what if we look at other stars? As we will talk about in our very last lesson, other stars have their own planets and their own little systems. And we're learning more about those every day. So a star and all the material that orbits it, that's the system. And for all the stars that are out there, that's a lot of systems. What do you think? There's going to be life out there? I think probably. So between the stars, there's not a whole lot, but we do sometimes find gas called nebula. Nebula can get very, very dense. These are basically gas clouds, but they can be huge, many, many light years across. Huge, huge gas clouds containing enough gas to build millions of stars. And indeed, in nebula is where we find star formation happening. This is a real picture. This is a picture of the Orion Nebula, which is gorgeous. And nebula are a very important place that birth stars. And we find quite a lot of these throughout our galaxy. So these are between the stars or interstellar clouds of gas and dust where stars are born. They're often called stellar nurseries. And all of this you find in a galaxy. Our galaxy, the Milky Way, of course, we live inside of it, so we don't really have a view like this. If you've never really seen the Milky Way, there's a reason why it's called that. It is a milky streak in the sky that we are embedded in. But this is kind of what, if we could see our galaxy from the outside, this is what it looks like from the outside. This is a spiral galaxy, and our Milky Way is a spiral galaxy. And you can see so many stars, they blur together. You can't possibly see individual stars. There's a graininess to this picture, which is just low res. And there's also a lot of gas and dust, which is what gives it a lot of its coloring. And interesting features like these dark streaks are mostly from dust clouds, which act a little bit like smoke clouds. There's a lot of galaxies out there. So as interesting as our Milky Way is, with hundreds of billions of stars, each with their own systems, probably planets, asteroids, and comets, right? Hundreds of billions of stars and systems within our own galaxy, and then there's many, many galaxies beyond that. We live in a very big place. So galaxies are great clumps of stars all spinning around, very interesting objects. And of course, we're going to talk more about these. All of this you find in our universe. The word universe means everything. It's just everything. So the universe is everything that we can see and everything that exists. And it contains probably trillions of galaxies that we could hope to observe. The universe had a beginning with the Big Bang that we will talk about. It may have an end, which is an interesting topic. But we're going to talk about, basically this entire course is about what is in our universe. And realistically, everything you ever learn in life is about what is in our universe. But in this class, we're going to take somewhat of a broader view. So what is your cosmic address? Right? Let's put this all in order, in structure. The universe, of course, is everything. So we start off in our universe. We can break it down into clumps of galaxies, big groups of galaxies that we call superclusters. And superclusters of galaxies, oh, these are big organizations. So if a galaxy is your house, the supercluster is a little bit like the neighborhood or the city even. And there's quite a lot of galaxies chained together in giant superclusters. Hard to even see them, they're so vast. Then you find smaller groups of galaxies. Our Milky Way lives in a small group that we call the local group. And there's not too much there, but that's our little group, our block. Then you've got the galaxies, and each galaxy has potentially hundreds of billions of stars. Our Milky Way has probably about 300 billion stars. It's quite a lot. They're smaller, they're bigger. Our Milky Way is probably fairly average. If you look into any of those individual stars in a single galaxy, then you'll find the star has its own system, as we said, with planets, asteroids, comets. You zoom in on a single planet orbiting one of those stars, and it'll have potentially its own moons and satellites. And all planets and all moons are very, very interesting, separate, and diverse. It's a big universe out there. So superclusters, the biggest of scales. I don't really have great pictures to show you of superclusters because that's such a big scale that you really have to zoom out quite dramatically to see it. Groups of galaxies. This is supposed to represent our local group. Our local group has two major galaxies, the Milky Way and Andromeda. Andromeda is actually the bigger one. Our Milky Way is not the center of the local group. It's not even the biggest member. And there's plenty of other spirals in there too, and lots of other littler galaxies. A single galaxy that we see here, this is a nice one. Our Milky Way looks, again, something like this. And this is a spiral galaxy. We'll talk more about those. You can see the spiral arms, which are very beautiful. The central bulge region is a lot brighter and whiter. There's less gas and dust in there. You can see these dusty streaks, right? And the central region is a lot cleaner. It just looks like one big light bulb, doesn't it? But it's not. It's billions of stars. But since there's no gas and dust, it just looks like a big, bright, white light. It all smears together. Very interesting objects, very complex objects. A single star, of course, is also a very complex and interesting object, and stars vary quite dramatically, as we will talk about. There are stars bigger than our sun, there are stars smaller than our sun, there are stars redder, bluer, hotter, colder. There's quite a range of stars, but they do all share certain features. They're all mostly elements 1 and 2, hydrogen and helium, producing their energy by fusing hydrogen into helium. There's a lot of similarities, as we will talk about. Around our sun, we've got the solar system, as we said, right? Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, and then out at the outer reaches, we've got the Kuiper belt of comets, and then even farther out, we have what's called an Oort cloud of very distant objects, so distant we've never even really seen one of them, but we can infer that they're there. So we're going to take a tour of our solar system for a couple of lessons later down the road. Here's a sort of a to scale picture. Very often, if you Google solar system planets or something like that, they'll give you a picture where Earth is just as big as Jupiter and Saturn, and that is ridiculous. Jupiter is, what is it, something like 13 times our diameter? It's huge. There's a storm, a single storm on the surface of Jupiter, the Great Red Spot. You could throw the Earth in there and it wouldn't even affect the storm. That's a single storm. So there's quite a size range, as we will see. And the sun, oh boy, the sun is 99% of the solar system by mass. It's pretty important. We do also have a lot of smaller objects. You may have wondered, why isn't he mentioning Pluto? It's because Pluto sucks, man. Pluto is dinky. It is teeny tiny. It's smaller than our moon, by far. In fact, it turns out to be one of many relatively large objects in the Kuiper belt. So it's basically just a huge comet. And in the asteroid belt, oh, did you notice this one? In the asteroid belt, there's similarly some larger asteroids. When they get to be a certain size, they become roughly spherical. We call them dwarf planets. They're on their way to being a planet, but they haven't cleared their orbit. They don't own their orbit. There's lots of other stuff out in the asteroid belt. So Ceres is not a planet, it's a dwarf planet. And there's lots of other stuff out there in the Kuiper belt. So Pluto is not a planet, it's a dwarf planet. This here, discovered in 2003, is now named Eris. And Eris is about the same size as Pluto, and it's when we discovered Eris that we started to have a problem with calling Pluto a planet. We'll talk more about that. Moons. We have a very large moon. We were lucky to get it from a chance collision. And that's a very interesting time in Earth's history as Earth was forming. So the moon orbits us, just like we orbit the sun, just like the sun orbits the center of the galaxy. There's quite a lot of motion out there. Everything moves. Everything moves. So there you go. That's a little bit of an overview of what's out there, right? A foundation to our course. Astronomy really is the study of the entire universe. Everything that's out there. We're going to talk about space and time, matter and energy. We have to talk about quite a lot of things if we want to understand all that. But it's very interesting stuff. It really is like no other subject. It gives us a perspective that no other subject can give us. All too often, we're very concerned with the little things. And that's not wrong, but it's worth understanding some of the big things too. The universe is After all, very, very vast, very amazing, and worth understanding. And this, again, by the way, this here is a real picture. It's gorgeous. If you get nothing else out of this course, hopefully you'll get a new desktop wallpaper background that you can keep and will remind you that yes, there are bigger things in life to worry about. So while I'm talking about things that are big, by the way, this is an astronomy course. We are going to do a little bit of math here and there to try and further understand what we're dealing with. And so we are going to have to work with some numbers that are big, all right? If I ask you to pick up 1 million pencils, you're going to have an interesting day, okay? Numbers get bigger and bigger and bigger and get a little bit hard to understand. What is 1 million pencils? Can you picture that? Because I can't really. I can picture 100 pencils, I suppose. 1,000 pencils start to get unwieldy. What about 1 trillion? How do we understand these numbers, right? If you wanted to count one number per second, 1, 2, if you wanted to count for 16 hours a day and then maybe get some sleep in, you can count to 1,000 in about 15 minutes. Yes, I dare you. So you can count to 1,000 in about 15 minutes. You can count to 1 million in about 2 weeks. I'm not going to dare you on that one. You have better things to do with your life, I think. You can count to 1 billion, and it would take you 50 years. So while 1,000 sounds like a big number, 1 billion sounds like a big number, there is a pretty big difference between these big numbers. One is, you know, a few minutes worth of counting, and the other is a lifetime, potentially. So we need to handle our numbers. We need to try and understand them, all right? And you can't count to 1 trillion. I'm sorry. You know, maybe we'll all be immortal. Maybe we'll be uploaded into robot bodies, and then yes, go ahead, you can count to 1 trillion. But as long as you're in a body made of meat, it's not going to happen. So we need to talk about how to deal with large numbers in this course, because we are going to talk about some, yes, astronomical numbers. And for that, we turn to scientific notation. So hopefully you've done this sort of thing before, but if you haven't, it'll take a little bit of review or a little bit of extra learning, but they're not really that complicated. So here, hopefully you remember an exponent. If you have 10 times 10, that's 10 squared, right? 10 twice, 10 times 10, not 20, 10 times 10, 2 tens gives you 100, right? So we can put different exponents on this. 1 10 is 10, 2 tens is 100, 3 tens is 1,000. Notice it's actually just 3 zeros, isn't it? 3 zeros. 1 trillion, so actually, by the way, this is important. 10 to the 6 is 1 million. You do need to know this sort of thing, all right? Sometimes it's called a mega. A megabyte is 1 million bytes, right? 1 billion, giga. That's 10 to the 9. 10 to the 9 is 1 billion. 10 to the 12 is 1 trillion. And that's 12 zeros, 3, 6, 9, 12 zeros. And that's, yes, starts to get into a pretty big number. And we will deal things. Like I've already said, that there's probably 1 trillion, 2 trillion galaxies that we could see out there in the universe. So we do need to deal with numbers like this. And so we do need these. It's easier for me to write 10 to the 12 than it is to write 12 actual zeros, right? So we're going to need to do this. A positive exponent, 10 to the, it's a positive number 12, tells you that there are 12 zeros, pretty much, okay? Small numbers are also going to be important in this course. Because what if I say how many, what fraction of stars in the galaxy are like our sun? It could be a very small number, right? So for that, we have negative exponents when it's divided by 12, or sorry, divided by 12, divided by 10. So divide by 10 twice, divide by 10, divide by 10, and you get 0.01. We've moved the decimal place from behind the 1. We've moved it to ahead of the 1, all right? So 10 to the negative 3, that's like a millimeter, or a thousandth, right? And so notice instead of having 1.0, we've brought the decimal place 1, 2, 3 ahead. Now we've got a very small number. A millionth, right? A micrometer, and now we've brought the decimal place 6 ahead, which means, by the way, yes, only 5 zeros here, because the how many decimal places includes the 1. A billionth, or a nanometer. It's an important thing in our world these days as we get to nanotechnology. So you can think of how the negative exponent, that's a very small number. How many decimal places, right? How many do you have to go back to get behind the 1? And you have to make 9 jumps. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, sorry, not that great with my mouse. But anyway, how many decimal places are in the number? So scientific notation is using that, and it is a way of expressing large or small numbers. It's a way of taking a crazy number, giving you sort of the number part of it, and then the power part of it. So if I give you this number here, 2,230,000, right? I could take the number part, 2.23, all right? Millions. 2.23 millions is 2.23 million, right? So 2.23 millions, and a million is 10 to the 6. So I can just call this 2.23 times 10 to the 6. And that's a scientific notation. This tells us it's on the scale of a million, and it's 2.23 millions, right? That's not a bad way to express a number, because you can do it for anything. For a small number, shift the decimal place back, 1, 2, 3. So this is going to be 9.5 times 10 to the negative 3. So let's say you've got the distance from the Earth to the Sun. That's, oh boy, how do I even say this out loud? 1,000 billion, so 150 billion meters, right? Is that right? So how are we going to do this? Let's bring the decimal place 3, 6, 9, and then 2 more. So it's going to be 1.5 times 10 to the 11 meters. All right. On the other hand, when we talk about something like fusion, we might need to know the mass of the hydrogen atom, and oh boy, that is a small number in kilograms. You want me to say this out loud? I don't want to say this out loud. I don't even want to think about what this is said out loud. Instead, let's just count. How many decimal places do I have to move back? 3, 6, 9, 12, oh boy, 15, 18, 21, 24, 27, did I lose count? 27, 1.67 times 10 to the negative 27 kilograms. That is a small number. But in astronomy, we're pretty concerned with hydrogen. It's the #1 element in the universe. So in astronomy, we deal with big numbers, we deal with small numbers, and in particular when it comes to distances, we're going to be using some special names, some special units. You may measure things with meters, right? Millimeters, centimeters, meters, kilometers maybe, right? But in the solar system, that gets a little bit unwieldy. Do you really need to know how many meters there are between the Earth and Jupiter? Instead, we're going to use something called the AU. The astronomical unit is the average Earth-Sun distance, which we already said is 150 billion meters, or 150 million kilometers, is the average. Okay, it does change. So the AU is a good scale, because if I tell you the distance from the Sun to Jupiter in meters, does that help you? And no, I don't know it offhand, but I do know that the distance from the Sun to Jupiter is about 5 AU. And that is helpful, because that tells me, hey, Jupiter is 5 AU. So 1 AU is the Earth-Sun distance. Jupiter is 5 times farther from the Sun than Earth is. That is useful, sort of, if you were dealing with that sort of thing, right? So the AU puts things in a scale that makes things useful in the solar system. Beyond that, though, the AU is actually not that big. It's only 150 million kilometers. If we're going to talk about the size of a galaxy, or the distance between galaxies, the distance to a distant supercluster, AUs are not going to help. Meters are not going to help. Instead, we turn to a really big unit, the light year. And the light year, LY, the light year is the distance that light travels in a year. Okay, light is not instantaneous. It travels at a certain speed, the speed of light, and it takes time to arrive to where it's going. It does travel very fast, though. So in a single year, light travels, oh, what is this? 9 trillion kilometers light travels. So in a single year, light travels 9.46 times 10 to the 3, 6, 9, 12, 9.5 times 10 to the 12 kilometers is the distance light travels in a year. That's a light year. That's what we're going to call it. That huge, I mean, what is that? 9.5 trillion kilometers. Do you know what that is? Do you have a feel for that? I don't. But if you tell me that that's the distance light travels in a year, that becomes useful. So make no mistake, a light year has nothing to do with time. I cannot measure a light year on my watch. I could measure a light year with the biggest ruler you've ever seen. A light year is a distance. It's the distance, it's the known distance that light travels in a year. And we're going to use that as a very useful meter stick out in space. Much more useful than an AU, for example, because 1 light year is already 63,000 AU. So even the AU, which is a huge unit, is not quite big enough to describe something like a light year. We're also going to use parsecs a little bit. And parsec is about 3.26 light years. We'll talk more about that down the road. There's a reason. It's a historical astronomical term. Consider a light year more like a meter and a parsec more like a foot, you know? Although it's more, I suppose, the opposite. But a light year is a useful thing. A parsec is a historical thing, a little bit like feet and miles. But it's only, 3¼ light years. So a parsec is similar enough to a light year in size. Anyway, so if we're going to talk about scale, again, you got to think about what's a useful way to describe it, right? We can describe things in terms of kilometers, and that's not so bad to a certain scale. But even the Earth-Moon distance, 384,000 kilometers. When was the last time you drove 384,000 kilometers? Do you have an understanding of how big that is, right? On the other hand, if I tell you that 30 Earths fit between the Earth and the Moon, well, that's a lot of Earths, but oh yeah, that's a slightly more tractable number, right? But as we get bigger than that, we need the other units. When we talk about the solar system, the AU becomes much more useful, right? Mars is at 1.5 AU. Well, that tells you where it is compared to the Earth, doesn't it? Neptune is at about 30 AU, right? Okay, so that's about the size of the solar system, 30 AU, right? So that tells you some useful stuff. So the AU is our key unit for describing the solar system, but we will get, again, much bigger than the solar system when we talk about galaxies and stuff like that, right? So 1 AU, 150 million kilometers, or 1.5 times 10 to the 8. Let's count that out again. 3, 6, 7, 8. 1.5 times 10 to the 8 kilometers, all right? When we get bigger than that, we need to use the light year. So for example, here's our Milky Way. Again, this is not a real picture. Why do we not have a real picture of our Milky Way? Because we live inside of it, right? It's not all that often you get to see a picture from above of your house when you live inside your house. You have to get a satellite orbiting or a plane way away from your house. Well, we've never gone that far from the sun. We have never left the solar system, really, okay? We have never explored our galaxy. So everything we know about our galaxy is from the inside. So here you see if our sun is located around here, and notice we're not in the center of the Milky Way. Did you think we would be? You really think we're the center of everything? We're not. Sorry. We are fairly average. We are fairly normal. We're located in the suburbs of the galaxy. This is a circle 6,000 light years. All right. Our Milky Way is about 100,000 light years across. It would take light 100,000 years to cross it. And to get to our next door neighbor, the biggest next door galaxy to us anyway, is 2 million light years away. The Virgo cluster, the nearest major cluster to us, 60 million light years. And other major clusters can be billions of light years away. And so if we're going to talk about the universe, galaxies, we need light years. So a light year, again, an AU is not all that big. A light year is quite a lot of AUs, right? So 1 light year is the distance that light travels in a year, about 10 trillion kilometers. That's a lot. Or about 63,000 AU, or about a third of a parsec, right? Although again, we'll talk more about parsecs later. We don't really need it yet. So in this course, we're going to try and keep the structure in mind. All right, all too often I've seen students who mix up the term universe, galaxy, solar system. And that's a little bit like mixing up. You know, it's saying my house is in Toronto is useful, but if you mix up your country with your city sometimes, then you're a bit confused. I don't think you know where you live if you don't know the name of your city, but you do know the name of your country and you think your city is Canada. That's a problem. So similarly, in this course, if you are mixing up galaxy, universe, solar system, that's a problem. We need to know the scale. We live on planet Earth, which is just one planet in the solar system around the sun. If you zoom out, then you find that our sun is one of many orbiting in the suburbs of our galaxy. And our galaxy is one of many. It's not even the biggest one in the local group. And if you zoom out from the local group, then you find an expanding universe of galaxies. All of them very different, very interesting. We need to know that structure to move forward. All right, so our solar system, we could talk about thousands, millions of kilometers, but realistically, the AU is much more useful, right? Once we leave the solar system, it's best to start talking about light years. The nearest star to us is 4 light years away. Our galaxy, 100,000 light years across. The local group, we're talking millions of light years in size. The universe, billions of light years is what we need to talk about when we talk about the universe. So here again, we see a scale picture to scale in size, but not in distance. All right, we will talk about the sizes and the distances of things. The planets are incredibly spaced apart. We need the AU to talk about them, but we can talk about the sizes of the planets in kilometers. All right. As for light, again, when we talk about light year, remember that's a distance. Light travels at a certain speed. So there's something else to think about here, by the way, which is that when something sends out light, it takes time for it to arrive, doesn't it? So think about, for example, a bolt of lightning. The bolt of lightning is relatively close. And so the light travels incredibly fast. It arrives basically instantly. You see it almost immediately. There's no real delay from the light from lightning. But the sound from lightning travels much slower, right? Sound travels about 300 meters per second, a kilometer every 3 seconds. And so if something is 3 kilometers away, the sound can take 9 seconds to arrive. And so there is a delay. You're hearing it after it happened. And so if you were blind and all you're doing is hearing lightning, then you're hearing the past. And that's worth remembering, the delay caused by the speed of light. The speed of light is incredibly fast. It's much more than 3 meters per second, or 300 meters per second. The speed of light is 300,000 kilometers per second. That's incredibly fast, 300,000 kilometers per second, but it's not instantaneous when it comes to the distances between something like stars. So light travels at 300,000 kilometers per second. To get to the moon, it's about a second. If you actually watch a video of the astronauts during the Apollo missions, you can hear an echo. They say something, and then about a second and a half later, you hear it again. And it's because their voice is going through their recorder to Earth, and then you're hearing it coming out of their earpieces. And there's a second and a half delay. So you can actually hear that delay. That's because their recorders are sending information at the speed of light, right? Which is not instantaneous. It takes a second and a half or so to go round trip from the Earth to the moon. The sun is far enough away that when it sends out light, the light takes more than 8 minutes to arrive here. We see the sun as it was 8 minutes ago, and if it blew up, we wouldn't know it for 8 more minutes. That's not a lot. Sirius, the dog star, the brightest star in our sky, that's 8 light years away. So light takes 8 years in time to travel that 8 light year distance. Okay, so let me say that again. 8 light years is the distance. That means light traveling is going to take 8 years of time to cross that distance. Okay? Light travels 1 light year in a year, so light travels 8 light years in 8 years. Clear? And so when we see Sirius, we're seeing it as it was 8 years ago. Probably hasn't changed much. It's a star, but nonetheless, we see it as it was. Andromeda, the Andromeda Galaxy, 2.5 million light years away, we see it as it was 2.5 million years ago, before humanity really existed. So we see things as they were. We see them, we see into the past. Astronomy is not just a way to see far, it's actually a time machine into the past. The farther away we look, the farther back we see in time. And this is a very useful tool for us. It can be difficult, it can be frustrating to not see things as they are, but to see them as they were. But as long as we remember it, it can be useful. So for example, Proxima Centauri is our next door neighbor star, and it is 4.25 light years away. So it takes light more than 4 years to get there. If we discovered aliens at Proxima Centauri and we sent a radio message, radio travels at the speed of light. It's a type of light, as we'll talk about next class. But let's say we discovered aliens there, we would send a message to them and we say, hey, nice to meet you. What's going on? That would take 4.25 years to arrive there. They would pick up our message 4.25 years after we sent it. They'd send back a message, hi. And that would take another 4.25 light year, or years of time to come back to us. And so 8.5 years have passed. How's it going? Nice to meet you. And they sent back, hi, 8.5 years later. It is the worst conversation you could ever have. All right, 8-year delay, 8+ year delay. So we are seeing Proxima Centauri as it was 4 years ago. Its light that it's sending now will take 4 years to arrive. Farther we look, the farther back it is, right? We see the moon as it was a second ago, not a big deal. We see the sun as it was 8 minutes ago, not really a big deal. We see Proxima Centauri 4 years ago. So when we look at the sun again, it's about 8.3 light minutes away. That's a slightly different unit, but it's the same idea. Light minute, right? The sun is about 8 light minutes away. How far does light travel in a minute, right? So if the sun were to suddenly vanish, we would have sunlight for 8 more minutes before we all, journeyed on into the apocalypse and died. So most what ifs in astronomy end with our complete and utter annihilation. So that's fun. Andromeda, again, that's on the bigger end of the scale, right, for now. Andromeda is a nearby bright galaxy, the nearest big galaxy to us, and it's 2.5 million light years away. So we see it as it was 2.5 million years ago. Right. When will we be able to see? When will we be able to see what it looks like now? 2.5 million years from now, the light that it's putting out now will finally arrive. Now, I gotta say, a galaxy is so big that it doesn't really change much in a couple million years. So it probably won't really look all that different. And realistically, it's close enough. What we see now is close enough to what it looks like now, but not exactly. And as we look even farther away, we will talk about all the way back into the past. There are things that we can see that are tens of billions of light years away. And so we are seeing them as they were. Here, this thing, whatever, this distant galaxy, this little thing, it's hard to see because it's 11 billion light years away. But that's something that sent us light 11 billion years ago, and that light is just arriving now. We're seeing something as it was 11 billion years ago, right after the Big Bang. All right? The more distant we look, we can see galaxies right after the universe was born. What was the Big Bang like? We can see it. So let's stop there for now. We're going to do our quiz now and sort of take it all up and make sure we're clear on everything we've talked about. We've got a lot of big things in this course. Big things. A lot of it's hard to understand, especially if it's new to you. And that's okay, right? Learning things that are hard, that's a good challenge. Maybe this course, astronomy, maybe it won't be a big part of your career, but learning difficult things, we all have to struggle and learn difficult things every now and then. So even if you're not super interested in astronomy, there's a reason to take a class like this, and it's to challenge yourself. Let's challenge ourselves. We're going to learn a lot of big things. We're going to learn a lot of crazy things, a lot of very interesting things. The first thing we got to learn is how light works. I've already mentioned a couple times some of the stuff to do with light. Light is how we do astronomy. And so our very first lesson, next lesson, we're going to be talking about how light works, how we do astronomy, how can we learn all what we know about distant stars, distant galaxies. Don't we just take pictures? No, we do a lot more than that. So we're going to learn about light, and that's going to help us learn how astronomy is done and how we know all the things we know. And we know quite a lot. And I look forward during the course of this semester to teaching you all about it. So let's get to it.